Now we are going to see a sequence chapter. So here we know what is a real sequence. Real sequence means it is a mapping from natural number to a real number. So the images will all be a real number. So that is said to be a real sequence. So now let us aim for the questions and as well as the theorems. Okay. So we will solve some problems for the exams, and also we will discuss on theorems. So if you are asked to say what is a real sequence, it is nothing but image will be a real number. So it is a mapping from a natural number to R. So you are assigning 1, 2, 3 with some real number. So f of 1, f of 2, f of 3 will all be a real numbers. Now let us see some examples. Let f is a real sequence and f of n is equal to n. So this mapping is assigning 1 to 1, 2 to 2, 3 to 3 in that way. So f of 1 equal to 1, f of 2 equal to 2, and so on. The sequence is denoted by the symbol n. It is also denoted by n over n. So you are varying this n, right? So this is a symbol for the sequence. Or we can write it as 1, 2, 3, etc. So this is how you have to first denote the sequence. Now for going into f of n equal to n square, this is another sequence, and you can write it as 1 square, 2 square, 3 square, and so on, like this like the set. Or you can denote it by n square. This is varying over n. So these are all some examples. So n by n plus 1 will be 1 by 2, 2 by 3, 3 by 4, and so on. Or we can replace it by like denoting by this way. Coming back here, least upper bound of a real sequence f of n is a real number m satisfying the following condition. So this is nothing but the upper bound. So upper bound definition we have seen this one. So this is like you know this, but the second point is making this to be a least upper bound. So yeah, if you are saying the sequence is bounded by some m, it is the upper bound. But if it also satisfies the second property, then it becomes a least upper bound. So least upper bound itself says among the upper bound you have to take the least element. So now you can say for each pre-assigned positive epsilon there exists a natural number k such that f of k is greater than m minus epsilon. So here you have to tend this epsilon to be so small. So it can be like 0. Okay. So it can be tends to 0, not exactly 0. It can be tends to 0 also. So if you are getting too close to the 0 also, this should be satisfied. So that means your m, whatever you have chosen, that m can be, if that satisfies, then that is said to be the least upper bound. So for each pre-assigned positive epsilon, so epsilon is always greater than 0. That is what they are saying. There exists this is nothing but there exists a natural number k such that f of k is greater than n minus epsilon. So let's note this point. Okay. Let's write what is LUB. So LUB is the capital M in R, for which f of n should be, you have to be careful what you have to write. So should be less than or equal to m for all n. And this is the first property. And second property, so this is the second property. It states that for all epsilon greater than 0, there is some k belongs to n such that f of k is greater than m minus epsilon. Similarly, you can write it for GLB. So here you are mentioning GLB as small m, which belongs to real number. It should satisfy these two properties. So first property is f of n. That is the sequence images. Okay. So f of n. So we can write sequence is nothing but f is from n to r. So f is from n to r. Okay. So f of n should be, so GLB means this should be bounded below by some number. That is for all entire n. So you cannot leave first numbers and all. Okay. Then for all epsilon greater than 0, there exists some k. So k can be 100 or 200 or second number, whatever. So such that it will be having same f of k. You are writing k because this from, may say k can be 100, then f of k. So after the k, it should all be lesser than m minus epsilon. So when that is satisfied, we can say that this is the greatest lower bound, and so if this is satisfying this property, then that will be the least upper bound. So this is what GLB and LUB. Now let's see what is the limit of a sequence. The limit of a sequence means this is f of n is a real sequence. So in some book they are saying xn. Okay, here they are saying f of n denoted by f of n, just a notation. So a real number L is called as the limit of this sequence f of n if corresponding to a pre-assigned positive epsilon, that is epsilon greater than 0, then exists a natural number k such that f of n minus L is less than modulus f of n. So here they are using the usual metric. So in general you can write it is in that particular metric. Okay, so f of n minus L is less than epsilon for all n greater than or equal to k. So after this they are just elaborating this modulus, and hence you are getting. So this is the explicit idea about what is the limit of a sequence. Here we don't, here they are saying there exists a natural number k. So this means there can be some first k minus 1, that is first 1000 or first 1000 power 100. So whatever can be anything, but after that particular k, this condition should get satisfied. That is, it is approaching to L means it should be satisfied. Let's say what is the limit of a sequence. So the limit of a sequence is nothing but, so let's take Sn to be the sequence. So you can denote it by any way. So this is the sequence of real numbers. So that is nothing but real sequence. Real numbers. So if Sn approaches to L, we can say that is Sn approaches to L. If so, you have to say this condition in order to say this. Okay, if means here you have to see first. So if for all epsilon greater than 0 there exists n naught in n such that we are representing it in any metric. So you are just using this notation. So Sn comma L is lesser than epsilon. So this is what okay, so here you have to write for all n greater than or equal to n naught. So after that n naught stage it is satisfying this property. So this is the limit of a sequence. So if the sequence is denoted by capital Xn or Fn, so you have to just change it accordingly. So you can write Fn or Xn or Sn. So anything is fine. So this is this definition for the limit. Let's see a theorem which comes after this. Okay, so a sequence can have at most one limit. So limit, we are talking about the sequence. Okay, so limit sequence, for this sequence you can talk only about limit, it's not limit point. So what this theorem says, this is the theorem, and what this theorem says is it can have at most one limit. So a sequence either can have no limit, or if it is having a limit, it is at most one. So that is, it can be only one unique limit. So here we are going to prove this. So this proof is by method of contradiction. So suppose if I am having a sequence of say f of n, so you can denote it by any way, okay, no problem. So suppose if my sequence so that is important, let my sequence, this is fn is a sequence having two distinct limit, because here distinct is important. So you are considering in a contradicted way. So limit L1 and L2, and without loss of generality, I am considering L1 is lesser than L2. This is quite important. Just, for the proof, it is important. So let me take this L1 and L2 as two distinct limit for a particular sequence. So I am just contradicting this statement. Okay. Before proving this theorem, I will just draw roughly about what I am going to do now. So here I am just going to construct in a way like, so since we are taken L1 is less than L2, I am just going to talk like this. It can be 0.1 and 0.10001. It can be so close, but there are still some points in between. So what I am going to take is epsilon. That is important. Epsilon is L1 minus L2 by 2. So for this confusion, I have written L2 is greater than, right? So L2 is minus L1 is less than 2. So here L2 minus L1 by 2. So this point will be something, and if you are doing like L1 plus epsilon or L2 minus epsilon, you will be arriving at this point. So what I'm just trying to say is like L1 minus epsilon is equal to L1 plus epsilon, because this is the epsilon gap and it is also epsilon gap. So L2 minus epsilon. So L1 plus epsilon will be in this point, and L2 plus minus epsilon will be this point. So now I am constructing like L1 comma L1 plus epsilon. This has a one of the neighborhood, and I am constructing another neighborhood called L2 minus epsilon comma L2. So these are the two neighborhoods, and I am constructing like these both are disjoint. So wait and see, this is going to be a contradict. This will come as a contract. So I have constructed in this way. So disjoint by choosing according to that I am choosing some epsilon. In this way I am just constructing one neighborhood and another neighborhood such that both of these intersection will be empty. So now you can see that is this one, and then after this here it will be this one. So let's say it is A and it is B. So for this I am going to use the limit because L1 is the limit for there exists K1 such that after K1 belongs to natural number. So after this K1 everything will lies in this. So here also same way K2 belongs to N such that I'm using this limit definition. So after K2 f of n all lies here. So f of n all lies here, f of n all lies here after K1 stage. After K2 stage f of n will all lies here. So if I am taking maximum of K1 comma K2, that is after this stages, f of n will all lies over here as well as here. That means and it will be presenting in between, and that is and in the sense I am using neighborhood of L1 comma epsilon. Here neighborhood of L2 comma epsilon. So this is the neighborhood of this one, and this is this. Okay, so this means my f of n is belonging to both of these, but by my construction both are disjoint. So that contradicts this theorem, and hence I can prove by contradiction. So I'm just going to take this expansion, that is f of n lies between L1 minus epsilon to L1 plus epsilon, and f of n will lies between L2 minus epsilon to L2 plus epsilon. That is, it is belonging to both the neighborhoods. It belongs to both the neighborhoods, but we have taken both the neighborhood as disjoint. So if this is going to present in both, it cannot be disjoint. So this is just contradicting. So hence we have proved L1 is equal to L2.